Hello, and welcome to session 3 of the Basic Statistics and Data Interpretation course. My name is Tim, and I'm going to guide you through this session, which is about statistical tests. In session 1, you learnt about different types of data. In session 2, you learnt about confidence intervals, p-values, and hypothesis testing. Now we will learn about some of the statistical tests we might use to test our hypotheses using different types of data. By the end of this session, you should understand the difference between paired and unpaired data, which statistical tests to use for different types of data, and how some of those simple statistical tests work. We can think of statistical tests as tools for testing hypotheses. We have to choose the correct tool for the job. This depends on the types of data used for our exposure and outcome, as described in earlier sessions, and also whether the data is paired or unpaired. Unpaired data is from groups that are independent. They are completely unrelated groups of people. For example, a random sample of people in Bristol and a random sample of people in Bath. Paired data, on the other hand, is when the groups are related in some way. This is sometimes also called repeated measures, because often it is about repeated measures at different times on the same people. For example, we might measure antibodies people have before and after taking a vaccine. Alternatively, measures might be at the same time point, but related, such as on the left and right eye of the same group of people. This table represents our toolbox of statistical tests. On the left is the data type of the exposure variable, and across the top is the data type of the outcome variable. So if you had a binary exposure variable, for example treatment A versus treatment B, and a continuous outcome variable, such as blood pressure, we would look across from binary on the left-hand side and down from continuous at the top, and see that we could do a t-test, which I will describe shortly, or a linear regression, which will be described in a later session. The tests highlighted in blue are discussed in this session, and the tests highlighted in green are discussed in later sessions. Let's start by thinking about two unpaired or independent groups of people. Imagine we have randomly allocated people to Group A and Group B. We've given statins to Group A and placebo to Group B. We want to know if there is a difference in blood pressure between Group A, who received the statins, versus Group B, who received the placebo. In this case, the null hypothesis is that statins are no different from placebo, and there is no difference in blood pressure between the two groups. Now, let's imagine that this null hypothesis is true. There is still going to be variation in blood pressure between different people. And this means it is highly unlikely that the average blood pressure in Group A will be exactly the same as the average blood pressure in Group B, even under the null hypothesis that statins do nothing. There will still be some difference by chance. We need to look at our data and decide if any difference we see between the groups is just due to chance, or whether there is a real difference between the groups. To do this, we look at the size of the difference in blood pressure between the groups and the variability in the measures of blood pressure. A small difference in blood pressure between Group A and Group B is more likely to be by chance than a large difference in blood pressure between the groups. Variability in the blood pressure measurements is also important. With high variability, we can see bigger differences between the groups by chance than when variability is low. This is the essence of the t-test. It takes the difference between the group means and divides it by the standard error in the data. Standard error is a measure of variability that you came across in session 2. Essentially, the t-test asks, how many standard errors apart are the means of the two groups? Larger differences between group means and smaller variability in the data lead to a larger value for t. Larger values of t are less likely to occur by chance. You will never have to calculate this by hand. Computer software will give you the t-value and the associated p-value. Let's return to our example where Group A took statins and Group B took placebo. Here is our table of results, with the difference between group means and standard error at the bottom. We have a binary exposure variable, Group A versus Group B, and a continuous outcome variable, blood pressure. And we use an unpaired t-test because the groups are independent. We can calculate a 95% confidence interval for the difference between group means using the standard error as described in session 2. We can calculate the t-value by dividing the mean difference by the standard error. And we can get the corresponding p-value from computer software, or also this can be looked up in statistical tables using the t-value and the number of people in our groups. Our t-value is -2 and the corresponding p-value is 0.0469. This means that the chances of seeing a difference between groups that is this big or bigger, given the chance variation in the blood pressure, is 4.69%, which is quite low. Also, our 95% confidence interval does not include 0. Overall, the data suggest that there is most likely a genuine difference between the groups. Now we look at a very similar example, but instead of comparing two different groups of people, we are comparing the same people at two different time points. So instead of comparing blood pressure for people who received statins versus placebo, we are comparing one group of people before and after they received statins. And here we use a paired t-test. Whereas in the previous example, we might have had 20 people in each group, so 40 people altogether. In this example, we have 20 people with 2 measurements each. This affects the calculation of the standard error, and that's why we need to run a paired t-test in this instance. As before, we can calculate a 95% confidence interval and a t-value and p-value, usually using computer software. The confidence interval does not include 0, and the p-value suggests only a 2.48% probability of seeing this result by chance under the null hypothesis. So we are fairly sure that statins do lower blood pressure. Now we'll consider a situation when we have 3 independent groups. Groups A and B take 2 different types of statins, and Group C take placebo. The outcome is still blood pressure. Going back to our statistical toolbox, we have 3 groups as our exposure. So this is a categorical exposure, the bottom row. And we have a continuous outcome, blood pressure. So this is the first column. So we can either run an ANOVA or a linear regression. Here we'll use an ANOVA. You'll learn about linear regression in a later session. ANOVA is short for analysis of variance. It is similar to a t-test, but this time there are 3 groups instead of 2. An ANOVA compares the variance between group means to the average chance variance within each group. I won't go into more detail about how this works here, but we can use computer software to produce an f-value and an associated p-value for the ANOVA. In this instance, the p-value suggests a 14.67% probability of seeing this result by chance. And this is not very convincing that there is a genuine difference in the blood pressure between the groups. Finally, we are going to explore an example with a binary outcome. We are interested in the proportion of people who have side effects following 2 drugs, X and Y. Proportions can be thought of as a binary outcome because each person either does experience side effects or they don't. We randomly allocate 120 people to receive drug X and 130 people to drug Y. 90 people have side effects with drug X and 40 people have side effects with drug Y. It seems very likely that there are more side effects with drug X than drug Y, but we want to run a statistical test to check if this difference is greater than by chance. Here we have a binary exposure, drug X or drug Y, and a binary outcome, they did or did not have side effects. So we can use a chi-square test or a logistic regression. I'll talk about the chi-squared test, and you'll learn more about logistic regression in a later session. To conduct a chi-square test, we start by creating a 2x2 table for our observed values. On the left, we have our exposure, drug X and drug Y. And across the top, we have our outcome, no side effects versus side effects. We fill in the cells, so you can see 90 people had side effects with drug X. Next, we create an equivalent 2x2 table for what we would expect under the null hypothesis that there is no difference in side effects between drug X and drug Y. If we assume drug X and drug Y are equivalent in this way, our best estimate of the proportion having side effects is the total number of people having side effects, that's 130, out of the total number of people in the study, which is 250. 130 divided by 250 is 0.52 or 52%. So our best estimate of the number of people taking drug X who would have side effects under the null hypothesis is 52% of the people taking drug X, and 52% of 120 is 62.4. We have to ignore the fact that you can't have 0.4 of a person with side effects in this case. Similarly, 52% of the people taking drug Y is 52% of 130, which is 67.6. We fill in the other cells of the table in a similar way. Now that we have our 2x2 table of observed values and our 2x2 table of expected values under the null hypothesis, we apply the chi-squared formula to each cell of the table. That is, observed minus expected squared divided by expected. Then we sum the resulting numbers to get our chi-squared statistic. You won't usually need to use this formula because computer software will do the chi-squared calculation for you. Here you can see the chi-squared calculation on an Excel spreadsheet. There is one row for each cell of our 2x2 table. For example, drug X with no side effects is the first row. There are columns for the observed, expected, observed minus expected, and observed minus expected squared divided by expected numbers. The final column is summed to produce the chi-squared statistic of 48.91, which has a very small p-value. It is highly unlikely that we would see this result by chance. As before, the p-value for a chi-squared statistic can be looked up in statistical tables, or more commonly is produced by computer software. A few things to note about the chi-squared test. It should only be used if 80% of cells have expected frequencies greater than 5, and if all expected frequencies are greater than 1. We use 80% here instead of a number of cells because chi-squared tests can be used when there are more than 2 groups. There are alternatives if cell frequencies are not high enough, such as combining cells or using Fisher's exact test, but I won't be going into those here. Applying what we've learnt about chi-squared to our e-cigarettes example, you'll see in table 3 of the paper that chi-squared was used for some rows of the table. In the row highlighted in yellow, we have the number of people who abstained from smoking after 1 month using nicotine or placebo e-cigarettes. And we see the total number in each group in the table heading. This allows us to construct our 2x2 table of observed values for nicotine e-cigarettes versus placebo and remaining abstinent after 1 month versus not abstinent. Once we have our 2x2 table of observed values, we can construct the 2x2 table of expected values under the null hypothesis that there is no difference in abstinence between nicotine e-cigarettes and placebo. We can then calculate the chi-squared statistic and the associated p-value. You can see that the p-value of 0.21 matches the p-value reported in table 3 of the article. And this concludes session 3 of the Basic Statistics and Data Interpretation course. Thanks for listening. I hope you found it helpful.